Hey, hi. Am I audible to you? Mhm. Am I audible? Mhm.
Can you hear me now? Hello, guys.
Hello.
Yeah, can you hear me now?
Yeah, I can hear you.
Okay,
Yes,
okay,
now you are audible. Yeah.
okay, okay. So, would you like to introduce yourself?
I'm Daksh. Completed my master's in physics.
Oh, I
Hi,
see.
and I am Tavinder. I'm a PhD student.
Oh, okay, great.
Yeah.
One second, let me just. Uh, connect my earphones.
Yeah, sure,
I'm
sure.
so sorry. So my earphones, my mic doesn't seem to be working. Yeah. Anyways, so what we are going to do is we are going to solve some problems here, and I would like to make this a interactive session. Okay. So you guys have any questions? Also, you guys solve the problems along with me. That would be better. And we'll interact along the way so that you guys. It will be helpful for you guys as well as for me also. Okay. All right. Cool. So let me present my screen and we'll start with some problems. Uh, okay. Can you guys see my screen?
Yeah,
Yes,
yeah.
yes, we can see.
Okay, great. Um, so you guys might have gone through the first week of the course lecture, right?
Yes, yes.
So the topics so it would be like some first 4 videos. Okay. The first video was like most of it was like introduction, what he was telling about his book and what are the portion he is going to cover and how intense it is going to be. The second part, he told about the second video had some introduction on Lagrangian dynamics, right? Lagrangian mechanics, like Lagrangian formalism. The third video had, and in Lagrangian mechanics, he told about, he first started with F equals ma, and he showed how you can come to the function called Lagrangian, which is kinetic energy minus potential energy, and what you can do with it, right? The third video had something on Hamiltonian formulation, formalism, and this one had uh, ideas about first about Legendre transformation, and the second thing he told about what Hamiltonian is. Hamiltonian is and how to go from Lagrangian to Hamiltonian, right? And how you can get Hamiltonian from Lagrangian. Hmm. And I'm sorry. Oh, shit. Yeah. And yeah, Lagrangian and Hamiltonian. The fourth video had something which was called as flows and symmetries. Here he talked about Poisson brackets, the constants of motion, and he talked about what the flow is, and he showed it for a case of for angular momentum, right? And this video ended with uh, the problem of the discrete how to go to a continuum if you have something, if you have got a discrete system. So discrete to continuous. So we are going to work on we are going to solve problems in these topics only. So what we are going to do is we'll mainly focus on these 3 things, these 2 things, and some part of these three things, this thing, Poisson brackets, constants of motions, and all these things. Okay. So the first question, which I would like to solve, is this. Okay, which is there in the assignment also. There is a particle of mass m, and it is in a gravitational field, and it is sliding along a ring of radius r that is spinning vertically on a table with angular speed omega. So we have to write the Lagrangian for this particle. All right. So you've got a ring of radius r. There is a mass here which is sliding on it, mass m, and this is in gravity, so there is acceleration due to gravity, and this thing is rotating also about this axis with constant angular speed omega. So we have to find the Lagrangian. So any ideas how to proceed? Hello? Yeah. Are you guys there? Hello?
Yes, yes, yeah, yeah.
Yeah, so any ideas how to proceed?
So we have to calculate the kinetic energy and potential energy here. We can use rotational velocity formula here, I think.
That is correct. That is correct.
Yeah, yeah, yeah. So from that we can get kinetic energy. Yeah.
Correct, correct. But first you have to figure out the generalized coordinates, right? All right. So what that means is, like, this is an easier problem, but if you were to do some difficult problem, where finding out the generalized coordinates, it's like, it would be for us when we solve problems, it would be those coordinate systems in which we can solve our problem very easily. All right. So for our case, we will take this angle theta. This will be our generalized coordinate. All right. And there's nothing else because the degrees of freedom for this mass is only one. Okay. It can only slide along the what do you say, the ring. It is rotating. If this velocity were not a constant, omega, if it was not a constant, then we would have another degree of freedom, which would be also phi. Okay, so if I take that angle to be phi, then phi would also be a degree of freedom. But since this has been given to us that omega is a constant angular velocity, so we need not worry about that. All right. Now, so yeah, so you need to figure out the kinetic energy, right? For this mass, for saying that. So how do we do that? Is there chat or something like that? Sorry. Oh. Yeah. Hello. Yeah. Yeah. So the people who newly joined, can you hear me and can you see my screen? I think I'm not being able to hear you. Hello? Yeah, Sindura, were you saying something?
No, you're audible.
Yeah, okay. So we're just solving a problem, okay? And what we were doing was we are solving this problem that there's a particle of mass m. It is in a gravitational field, and it is sliding along a ring of radius r, and which is spinning vertically on a table, and it is spinning with a constant angular velocity omega. So we have to write the Lagrangian of the particle, and we were discussing about this. And before this, I just talked about what were there in the course content of the first week, like something about the Lagrangian, Hamiltonian, and something about symmetries. Okay. So we have to solve this problem. So yeah, so I was doing this thing. So you can use as one of you was saying that we can use this half I omega square, that formula. I mean, for the writing the rotational kinetic energy formula to write how this thing is moving. So let's go with that only, okay? So if this mass moves in this direction, the theta direction, if it is moving this way or that way, for that part, you will have the rotational kinetic energy is half I, and I for us is like mr square, and the angular velocity in this direction, which is just theta dot square. Okay. Now, since this is moving in this direction also, you're going to have to write another kinetic energy. There will be one more rotational kinetic energy, which will be I2 half I omega square. Now this omega square is this omega, because this is the kinetic energy of the other direction, rotational kinetic energy. But the I will have some changes. And the reason is because your axis is this axis, say A, and it is moving around this axis, right? So your effective radius is this. So how do we find that? This is theta. This is r. This is going to be pi minus theta. So this is like 180 minus theta. And you take r of this. So this I, whatever I am writing here, is equal to m r cos of t minus r square of that, right? Now, so what is cos 180 minus theta? It's just cos of that only, right? So your I2 is So you have found the total kinetic energy, which is I1 plus I2. Is there anything more? Yeah. Do you think, is there anything more here? Anybody? Okay. So now we have got to find the potential energy. So to find that, first you'll fix the zero of the potential. Okay. So if you fix the zero to be, say, here, then you'll have this. Sorry, sir. So then you'll have to say you have to take this distance, because this is the distance which the mass is above the ground, right? If you take the zero of the potential to be here, you just have to take this distance. Okay, depends on you. So I'll take zero to be here, and if I take it to be here, this distance is wait, I might have made a mistake. Wait, pause. I'm so sorry. This is yeah, this is 180 minus theta. I wanted this distance. Okay, I'm so sorry. I wanted this r, and this r is actually r sine theta. This is actually Mars. Now, yeah, now we want this distance. I'll call this distance as z. So z is just equal to r cos 180 minus theta, and this is equal to minus of r cos theta. Okay. So our potential energy is equal to minus Gz is equal to mg r cos theta. Right. Since z is negative, so we will have therefore our Lagrangian will be t minus v. There's a minus sign here because the direction is minus z actually. So there will be a minus sign here. So z is negative, right? Because this is 0 for us. So t minus v will be okay. Any doubts? Hello? Okay. Okay, great. Then let's carry on then. Yeah. Uh, Let us do another problem, something like this only. And this time we'll do particle moving in a cone, okay? So you will have a particle of mass m and it moves in a surface which is a conical surface. So let's do this. Yeah. So you have a particle okay. And this, we'll call this direction as rho, and the mass is somewhere here, and the mass can move only inside this cone, okay? Mass can move only inside this cone. This is the z coordinate. And now what you have to do is you have to find the Lagrangian for this one. All right. This angle has been specified to you. This is a constant angle. This is alpha. So can you tell me how to go about it? Can anybody tell me? Hello? Okay. Anyways, am I am audible to you guys, right? Like, because it's very hard to realize in this online thing. Can any of you just give a response? Okay.
Yes, sir, audible.
Oh, okay, okay, okay. Yeah. So, yeah, it was you, Daksh, right? Can you just say how to go about this problem? How would you solve it?
We have we have to represent the position of the particle in probably two generalized coordinates. One being
Hmm.
its distance
One being what?
from one
Yeah.
being its distance from the top,
Hmm.
of, and another probably its angle with the vertical.
Angle with the vertical. Yeah, you can do with the angle too, but we'll not go with the angle. We'll use only rho and z, okay? So one is for the particle moving up, one is for the particle moving inwards, outwards from the cone, okay? If we do this, we don't need the angle at all. Huh? All right. Actually, there is a relation between these angles z and rho, right? So it's if you write, say, tan of alpha, you have, say, this is some rho, and you have z. Okay. So if the particle is just constrained on the cone, you can use this relation. There is only 1 degree of freedom. If this particle is inside, wherever if it is somewhere inside, then you have 2 degrees of freedom. By the way, you are correct, Daksh. I will use angle only. This is easier. Yeah, you are correct. So this alpha is the constant alpha. This is called the full this thing, right? Now I'm going to write another this thing. This is beta, and I'll do it clearly here. If the particle is say somewhere here, and it makes beta angle. If it is rho, if it is z, now you can relate z and this thing, right? Z and rho. So you're going to have tan beta as 2 by z. So this implies that z is rho cot beta. So you found z. You can now easily write what is z dot. Going to take rho dot cot beta plus. Sorry, I write it better. Z dot is rho dot cot beta plus rho. What is the differentiation of cot? You remember? Minus cosec square, right? Okay. So if this was a constant, okay, if this mass was moving on just the surface of the cone, then you would not have this term, right? Because beta is fixed and it is a constant angle alpha for you then. Now you will write the kinetic energy, which is half m rho dot square plus there's this angle. So we are doing this thing in actually cylindrical coordinates. Yeah, cylindrical coordinates. This angle I'm going to call phi. So I have rho square phi dot square plus z dot square. Now you're going to just have to substitute this here. And then this. This cos square is cos x square. Now for the potential energy, you put your 0 here and you will just have mg z. And this time you will have mg z. So, and z for you is rho cot beta. So you found your Lagrangian, T minus B. Okay. Any questions? Okay, no questions? Okay. Okay, let us take a, let us pause here. And yeah, I should have asked everybody before starting the class, do you have any doubts in the lectures? Like whatever from these 3 lectures, these Lagrangian, the first 4 videos. Okay. I guess
Yeah.
you have no doubts.
Yeah,
Yeah,
sorry. So I had one question. I think it's regarding variational principle. I don't know it is the variation principle you are covering here or not in these
variational
topics.
principle.
Yeah, yeah.
The variational principle is covered in the Lagrangian mechanics part only, right?
Yeah,
We are
I
saying that
think, yeah.
the Euler-Lagrange equation.
No, I think it was some derivative and there was some, hmm,
See.
okay,
Yeah, what was it? What was it exactly?
dynamics of continuous system. Are you covering here? There was a functional derivative.
There was functional derivative. Yeah, there was functional derivative. Yeah, this
Yeah,
was
yeah.
in the part, he taught it in this part only, right? Functional derivative.
So you will cover here this or the next week?
Oh, I'll cover it here. Wait,
Yeah.
let's.
Okay.
No. Wait a second. So, actually, first I have to cover all your doubts. Then I
Mm-hmm.
will go into problems. Okay. So for
Okay.
the
Okay.
functional derivative part,
Mm-hmm.
I have not made any problems as such, but I can make a
Mm-hmm.
problem right here, right now, and help you, with your doubts.
Yeah. Yeah. Sure. Sure.
So first of all, just tell me like if you are clear with the idea or not. The functional derivative, it's fully, this is a mathematical tool, okay? But we use the idea of functional derivative where you see something like this, right? ds by dq,
Yeah. So actually,
x
I
or
have.
something like that.
Sorry. Sorry to
Hmm.
interrupt you. So I
Hmm.
had question from that particular integral he performed.
Hmm.
Uh, the integration by parts. I think it's equation. Let me check.
Oh, okay. Wait. I also have to open the video. Okay, wait a second.
Oh,
Let me just. Okay, just tell me
I will tell you
exactly.
the.
Tell me that. Yeah. Tell me the time. Yeah. Tell me this thing. Yeah. Equation from his book.
Okay. Okay. Yeah. Sure. Mm-hmm. No.
Let's open it.
Yeah. It's equation 1.56.
1.6. Okay.
Yeah.
Yeah.
So
Okay.
here,
Let's.
yeah, you can discuss this there, and let's see.
Okay. So equation. This is his book. Equation 1.56. Del of del gx h of g of take any variable y, suppose. Here he has taken s, right?
Yeah,
Ah,
yeah.
no. There. Yeah, okay. So the integral a to b ds. Oh, sorry. Wait. I have to start this. H of g of s is equal to half to b ds. So it's like this, okay? G prime of s, then whole square. It's written it very weirdly there. And where G prime s is this. Now we are going to take a functional derivative of this object. One.
Yeah, yeah.
So it's equal to half. Since you are taking the functional integral, and since it is x and not s, you can take the integral inside and then differentiate on this. Okay?
Yeah, yeah.
Okay. So you're going to have this. Hmm? Then the rules of functional integration, they're same as the rules of ordinary calculus with some differences. So in this case also, what you're going to do is you're going to first use the rule which you had seen probably, like ddx to the power n is equal to nx n minus 1. We're going to use a similar rule for the functional derivative case. So that will give you 2 g prime s. Now we are going to use this is this part. Now we are going to use the chain rule here. And that will give you x. Okay. So you are going to get b. So g prime s is dgds. Okay. Now again the same idea. This is x, this is s. This can go inside. So you will have something like this. Now this object is Dirac delta. That is by the definition of the functional derivative, okay, which is given in equation 1.54. All right. So we are going to have this integral as a to b ds dg ds s ds Dirac delta of s minus x. Now you are going to perform integration by parts. Now here is a little tricky thing, okay, which he has not said in the book actually. So AB ds dds of okay, minus Is this correct? Hello? Hello, Tavinder it was, right?
Yeah. Sure.
Is this correct? The equation which I have written, this equation number 2, I have marked it for you.
I have to check with the notes book or
No. Dekho.
okay.
Like, look. So you differentiate this first, then
Mm-hmm.
you will get d square this thing into this thing. So just this thing is this is by using product rule, right?
Yeah. Okay.
This part. Huh. Now this subtraction, this will cancel, right?
Mm-hmm.
You have this term also, this will cancel. So you are getting back the same term which was there. This term which was there, right?
Yeah.
So this formula is correct. 2 is correct. Now, the second part is, so the first part is a total derivative. And the second part is, so I have splitted the integral in 2 parts. Okay. Now you just invoke the Dirac delta. You are going to get the second term. The first term is by fundamental theorem of calculus. It will just be the boundary values. So this is, now I'll write this as G prime and this as G double prime. Huh?
Mm-hmm.
So this is G prime of B Dirac delta of B minus X minus G prime of A Dirac delta of A minus X. This is the integral evaluated from this part. Minus, you do the Dirac delta integration here, and you are going to get, and you'll assume that, this thing is between A and B. Otherwise, the Dirac delta will be 0. So S minus X is between A and B. Then you are going to get d2g by dx square, x square, x. This can also be written in notation as like this. Okay, there is this term, which is not written there. Okay, are you with me? Hello.
Yes. I'm with you. Yeah.
Yeah, there is this term, okay, total derivative term, which he has not written there. Yeah, which he has not written there. Okay, so the way in which he is making it 0 is probably by thinking that G prime B is equal to G prime A is equal to 0. All right. Hello.
Yeah.
Yeah, this can be one of the ideas. The other idea is like, even if there is no integral here, the Dirac delta only contributes when your x is b. So for this part, when your x is b, and for this part, when your x is a. Okay.
Yeah.
So in a way, this is also being thought that, X is neither A or B. Then also this term can be thought to be 0.
Yeah, now you clarified this for me. Thanks.
Okay.
Yeah.
Okay. Great.
Yeah, thank.
Any more doubts?
No. This was the only doubt. Thanks.
Okay. Great. Anybody else? Any doubts? Hmm. Okay. So we did this. We did this also. Did this. Okay. So let us go to. So you guys have any problems which you were solving, which you tried to solve but could not solve? We can also discuss that here. That would be like really great if you have something like that. Okay, then leave it. Yeah. So let me check. So what's the problem? Yeah. You guys. Okay, I'll give you one problem. Okay, take this as a homework problem. I'll just give you 3 steps. This problem is taken from a book, and this problem is similar to the cone problem. So what you have is yes, three, right? Sorry. Uh, there is a bowl like this, and the this is Z, and the equation of this surface is given as this: Z is equal to half x squared plus s. This is the surface of the bowl. It's given by this equation. This a is some constant. You may take it as 1, and a particle is moving here inside the bowl. Okay. So find the Lagrangian. The way to solve it is the same as this. You just have to relate some these things. Here you use cylindrical coordinate systems. Spherical coordinate system to solve this problem. R theta. Yeah. And the particle is just moving on the surface. Okay, it's not moving inside. So R will be a constant. There are only 2 degrees of freedom in this case. Yeah, this is a homework problem. Okay, and I'll just give you some steps so that it's helpful. So yeah, no, better do it. You guys can do this one. Sure of it. Let's move on to different type of problems now. We solved a lot of things in Lagrangian mechanics. Let's go to Hamiltonian formulation. In this Hamiltonian formulation, I'll give this problem. So suppose the Hamiltonian of a system is given as p square by 2 alpha minus b q t Okay. Now you have to find the Lagrangian for this one. So this Hamiltonian is a function of P and Q. And this Lagrangian should be a function of Q and Q dot. So how to go about solving this one? Anybody, any idea? All right. Okay. The way to solve is by using the Hamilton's equation of motion. Del H by equal to S P by H by this thing, this, uh, by H by. So we are going to use this equation. So Q dot is equal to, just differentiate it from here, P by alpha minus PQ to the power minus alpha t plus is divided in problem form. Okay, it is. So you write Q dot in terms of P now. Sorry, P in terms of Q dot now. That is Q dot plus dq to the power minus alpha t times alpha is equal to P. Now so you have done this inversion. This is the inversion. That means we have written, we had first Q dot in terms of P, writing P in terms of Q dot now. So Hamiltonian Lagrangian is P Q dot minus H, where P is dou L by dou Q dot. So we will substitute for this thing, Q dot plus dq e to the power minus alpha t alpha dot minus, oh wait, this will be a very big thing. So instead of this, no, we'll substitute for Q dot, sorry, because that will be easier, because H has all P square and all these things. If you take square, you have to break this thing and it might be very big. So Q dot, let's substitute Q dot and then change P in terms, write P in terms of Q dot towards the end. So this term and this term will make this P square by 2 alpha minus bqp to the power minus alpha t plus this term and this term. This term cancels with this term. And there is d alpha by 2 this way. Alpha 2 this way alpha 2 this way alpha 2 this way. So now we have to substitute P and write it in terms of Q dot. Q dot plus dq e to the power minus alpha t whole square alpha square by 2 alpha and all these terms. Q dot square plus 2 q dot to the power minus alpha t plus b square q square to the power minus 2 alpha t by 2 minus b alpha square by 2 b square to the power minus alpha t plus b square alpha by 2 q square. So let's see which terms cancel. Q dot e to the power minus alpha t q square or minus 1 alpha 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 alpha. So this term cancels with this one. And we get alpha q dot square by 2 plus bq dot to the power minus alpha t minus b alpha square by 2 q square minus alpha t minus dq square by 2. So I think it doesn't solve more than this. Let me just check this is correct. Yeah, this is correct. So this is the Lagrangian, which we find from this Hamiltonian. Okay. So any doubts? Any questions? Anything here? And are you guys solving the problems as I'm giving the problems to you? Yeah. All right. Okay. Let's do one difficult problem. This problem has got, so this is the second problem in the, and this one has got some Poisson brackets calculation. So yeah, I have the Lagrangian half m x dot square plus y dot square plus z dot square plus some EB by 2c x y dot minus y x dot. Your question is evaluate x dot leave x dot x dot is a multiplication and so since there is h and we have to find h first in this problem. And then we have to calculate the Poisson brackets. So Poisson brackets, if you remember, A, P, Q, B, P, Q is equal to dou A, dou B, dou Q, dou P, dou Q, dou P, dA. Okay, this is the Poisson brackets. And yeah, let's find the Hamiltonian first. So we'll find the Hamiltonian like we had found for the earlier case. So we'll have to first find Px, which is equal to dou L dou x dot, and this equals mx dot minus Eb by 2c to y. Ui dot pz equals pz equals pz. So why are we doing this? We're doing this because we want to substitute in the expression of Hamiltonian, which is summation I, in our case I is xyz, pi, and qi minus L. Q dot, and you have to substitute q dot of p. And your q's are qi actually. So That means, first of all, you have to substitute q dot in terms of t in your Hamiltonian, in your Lagrangian. So that means you've got to invert these formulas. Okay? That is x plus d by 2cy. Mm. Now you substitute this in your Lagrangian. Junction q comma q dot of p is equal to this is the first term plus x y dot y x dot. Then by 2m px square plus py square plus pz square plus 2pxy pb pb by c pxy. The 2 gets cancelled with this 2. Similarly, pxy plus pyx. This thing comes from the other term. Here too you have the same thing. This mistake. I understand the mistake. Del by del x dot to the minus y Is a plus x. This is a plus x. I'm so sorry. So this is a minus. Plus b by 2mc. It's py minus ypx minus b by 2c by 2c x square minus plus minus square. This is our value of now we are going to do this. We're going to find h. H, as I told you, it is px. P dot minus x dot plus y dot s z minus this big L q of q dot q. And I'm going to substitute for x also. You be able to see y and dy minus db by 2c x plus pz square by z dot is z square by e minus L. So we have t square capital N plus py square capital N pz square by 2n. These are these terms. At first, this and this term with these terms plus. Now we have to see what cancels and how it does. Pxy, but there is a 2 here, and there's also a 2 here. So this term should cancel. Just check. I'm going correctly on it. So yeah. So this term cancels, yeah, that is correct. And there's a minus sign here, but there's a plus sign here. There must be a sign mistake. So anybody, are you also doing this problem with me? Hello, is anyone there? All right. Let me fix it. Don't it's not. I think I've made a sign mistake somewhere. So I'm getting something which is weird. So I think, okay, let me take a new approach to this problem. I think that will make the calculations easier. I shouldn't have gone this way at all. It's in the Lagrange. Instead of doing this, I'll substitute for P and then I I was actually being a bit methodical in doing it, but it seems that it's just making it lengthy and difficult. So I'll do it, and maybe I messed up somewhere in the algebra. So I'll do it in a different way now. So I'll directly use H is equal to Px not plus Py is L, and we'll substitute for Q dot later. We'll first substitute for P itself. We'll substitute for P itself. So, minus So these terms will give a positive sign. So we are going to have half m dot square plus y dot square plus z dot square. Now we have a minus EBYX dot by 2c, and we have the same term EB by 2c yx dot with a plus sign, so these terms will just cancel. So these terms, they will just cancel. So this term cancels with this term, and this term cancels with this term. So what we are going to have is just this term. Yeah. Now this was so easy. So I was just putting L, calculating L first, and that was going too big, and I messed up the calculation somewhere. So now we'll just substitute that one. X dot is this thing, and we're going to substitute this. X plus B by BC. Then this will give a, this factor will give a, this will give 2n. So 1 by 2n of this thing. So this is our Hamiltonian. Now we are going to calculate x dot and y dot, this Poisson bracket. So for that, we just need this substitution, and we are done. We can calculate. So okay. So you're going to have ddx of this thing. Let me call this A, and let me call this B. Then you're going to have ddx of A ddx of B minus ddx of B the same with y. Now you just differentiate and substitute. This is dx of 0 minus, we have minus plus dy to c, and this is just 1 plus del a by del y, this is dy to c, dv by dpy is just 1, and this part is 0, so you have d by c. Let's check if this is correct. Mm, yeah, this is correct. Now let's calculate the Poisson bracket with the Hamiltonian. Uh, you have to calculate this term, mx dot with h. Into h is 1 by 2n let's compute for this thing so that and h, so that we don't have to worry about this factor. So now you have got to do the same thing. So del a by, suppose this is a, this is b, del a by del x is 0. So del a by del x is 0. Del d by del tx is, yeah, doesn't matter. We have something like the same formula as above. But overall machine. qi would be that change this. Now del a by del x is 0 plus del a by del y is ed by, okay, del a by del x is the only x part. Okay, first I will write the x part. So del a by del x is 0, so this term is 0, minus del b by del x, it's not 0. We have 2 y minus by 2c times x by 2c times b by 2c with a minus sign. del by, this is del by del x. Yes, del by del y is non-zero, so we have e by 2c there, times del b by del py, which is also non-zero, which is this 2py minus this is for x del a by del p, which is so del a by del x was 0, so this term is 0, and del b by del x is 2py minus ev by 2c times minus ev by 2c into del a by del px, which is just 1. Okay. There's a 1 here also. And then this is for the y part. So for the y part, del a by del x is ev by 2c, and del b by del py is 2py minus ev by 2c times x. Uh, minus del b by del y is del b by del y is 2 px plus b by 2c y minus b by 2c. Sorry, yeah, del b by del y. This is del b by del y, and del a by del py, and it's just 0. So this term is also 0. And we have pz also. So just see what happens. But this term will be 0 in this. That we can see by del a by del z is 0, and del b by del z is also 0. So this last term is also 0. So we have two things here. We have this thing, which is b by c ey minus b by 2c z plus so we have b by c ey minus b by 2c times x. So yeah, let's just see if that is correct. Let me see. Yeah, this is correct. There's a problem with the factor of 2. Oh, they had a 2n, so we don't have a 2n. So this is right. So we are done with the problem. In other words, you may remember the equation, this equation, del t, anything here is equal to, where a is a function of pq, and it can also be a function of t, is equal to del a del t plus the Poisson bracket with h. Now, if a is not a function of t, then this term is 0, and A would be a constant of motion, that is dA is equal to 0 if the Poisson bracket is 0. So in our case, we see that dx by dt, dx dot by dt, if we naively think about this thing, we see that x dot is not a constant of motion, and that is what we expect also. X dot has something to do with velocities. All right. Any confusions, any doubts? Sorry for taking a lot of time on this problem. Are you guys there?
Yes, sir.
Okay. Okay. Any doubts? Anything? Any questions? Anything which you want to ask? Which there's nothing. Okay. I've also run out of problems, to be honest. Like, uh, so okay. Let me give you a problem in. Let me show how to solve some problems in functional derivative. I think that would be better. Hmm. Mm, Suppose I give you uh, mm, yeah, suppose hx is h of x is equal to okay, let's do this. S of q of t is given integral some a to b L of q of t q dot of t dt. Now you have to find what is del s by this is probably not easy, right? Del q of this. So now this we know this is the this equal to 0 will give you the Euler-Lagrange equation. But we'll try to solve this using the ideas of the functional derivative which we just learned. Okay, that is taking the limit which is there in the book, which is limit epsilon going to 0 s of q of say plus t prime plus epsilon Dirac delta t minus t prime minus s of q of t prime by epsilon. Okay. Can you guys work out this along with me?
Yeah, sure.
So use this definition. So we are calculating everything from the first principle. You have to find this, and you have to find, you have to subtract with this term, yeah, and then divide by epsilon, and you see what you get. Okay. Let's find this again. S of t prime. So so there is a derivative. Hmm. So I will do the Taylor expansion, which will give me do L Q 7 plus Q dot 7 T dot. Let me remove this thing, the other part. Plus this thing plus order epsilon square dt prime. This implies okay, this part we are going to only this part is nothing but S of Q of T prime plus the other part is this, and we have it to be dou L by dou Q with epsilon Dirac of T minus T prime plus dou L by dou Q dot epsilon dt. So you take the epsilon out and you subtract this 2, so you are going to get this, which is S of Q S. You have order epsilon square also, okay, here. Dt. So you have S of Q of T prime plus epsilon Dirac delta of T minus T prime minus S of Q of T prime by epsilon. You're taking this epsilon downwards. You're going to get to be dou L by dou Q Dirac delta T minus T prime plus dou L by dou Q dot dt divided by t minus t prime plus order of epsilon now. So, so this can be further massaged into so you'll get a so I'll break this term. I'll do integration by parts. So I'll get two terms. One is this term, which I club together with the Dirac delta. And the other term is a total derivative term. Plus order epsilon. Now you will take the limit. Limit epsilon goes to 0 s of q of t prime this equals, you also have to take the limit here. So when you take the limit, since this term doesn't have any epsilon and the integral is assumed to be well defined, so this limit can go inside and it will only hit this, and epsilon goes to 0 since this is linear, so all these terms will be 0. So you will have this term is equal to a to the so what do you get? You get ASQ of t prime t is equal to this thing. Okay, any doubts? Any questions? Okay, now this is just a mathematical, whatever I have done is just a mathematical thing. Okay, I have never said that this S is action or this L is Lagrangian or something like that. But if you are to say that this S is action, this L is Lagrangian, and so on, this L is Lagrangian and so on, then you have to, you will invoke all these things that in the endpoints, the variation is 0. So you are going to say this is the boundary term, and on the boundary, this term goes to 0. You are going to say that the variation is 0. So you're going to say that this term is going to be 0 at the boundaries. So you will remove this term by that argument. Okay. And then you are going to do this integral. T minus t prime is there. T minus t prime is there. You're going to do this integral. And after doing this integral, remember you had this derivative was with respect with q of t. Okay. So you will have all your q of t substituted by q of t prime. And you say you invoke the principle of extrema, the variational principle, and you say that for this trajectory the variation in action should be 0. Then you will get your Euler-Lagrange equation. That's the way to proceed further. Okay, to get the Euler-Lagrange equation. But till now, whatever I have done, whatever variation I have done, is just a mathematical formalism. There is nothing it's like no statement about action or Lagrangian or something like that. It's just an exercise to see how the variational derivative works. Okay, I think it's about time. Anybody, any last questions or something like that? Yes, no? No questions?
No.
Okay, all right. How was, did you find the class? Okay, let me just. So I'll stop the recording. It's already late. So how was the class? Was it fine according to you guys? The feedback of the class. I would love some feedback.
For me, it was good and nice. Yeah.
It was good. Yeah. Great. Daksh, what about you?
Yeah, it's a good question.
It went well for me.
What?
It went well for me also. I think so.
It was not.
It went well for me. I think
It was not good for you.
it went well for me. It was good. I mean,
Oh, okay. And the third person, I can't see your name. I'm sorry. It's
Sharath,
yeah. Hello, I can hear you. Yeah. How was it?